Thank you for coming to my talk. In this presentation, I will show you a case study to apply geothermal double difference FWI in a steam chamber study. I will also present a practical workflow to apply geothermal travel time tomography and FWI in 4D VSP processing. This talk will take about 15 minutes of your time. Hopefully you can carry away something new at the end. I will first review geothermal's capabilities in 4D seismic processing. Then I will present geothermal's double difference technique and explain why it will be more efficient and stable than single travel time tomography or FWI in time-lapse processing. I will use a field data example as a case study to show how we delivered a high-resolution view of a complex steam chamber 3D imaging. For 4D VSP, I will use a 3D checkerboard model to present geothermal's workflow on how we build accurate 4D models to monitor the velocity changes. Geothermal 4D processing can handle cross-well seismic data. In hydraulic fracturing, cross-well seismic monitoring can provide greater insight into the nature and geometry of the fracture network and its development within the reservoir. For more information about geothermal cross-well seismic processing capabilities, please check out our software package, Tomo Pro. Carbon capture and storage is considered one of the options for reducing CO2 from heavy industry by depositing it in an underground geological formation. The Time-Lapse VSP can provide a solution to monitor CO2 diffusion range. Geothermal provides a VSP processing software package called GeoVS. It has a user-friendly interface with most advanced technologies. 4D surface seismic data can assess changes in producing hydrocarbon reservoir with time. Geothermal GeoThrust is a comprehensive processing software package designed by Dr. Oz Yilmaz. If you want to have a live chat with Dr. Oz, please visit our virtual booth or enter for a drawing of his book. Before I show you our 4D surface seismic data case study, let's review a key technique we apply in the processing. Let's start with the travel time tomography. Travel time tomography is to derive a velocity model by minimizing the difference between the input data, which is typically the picked time, and then synthetic data, which is generated from a forward retracing using a model. We can perform the tomography for the baseline survey and then monitor survey separately. I call the workflow a parallel workflow as illustrated in Figure A. Or we can use the model we derived from the baseline survey as starting model in the monitor tomography. As illustrated in Figure B, I call Figure B a sequential workflow. In this way, we can reduce the number of tomography iterations in the monitor model update. However, in both the parallel workflow or sequential workflow, even if there's no difference between the baseline input data and the monitor input data, we will still see a model difference in the tomography results. Just like if we continue to run more iterations of tomography for the baseline itself, we can continue to push down the misfit between the input data and the synthetic data and get a new model from more iterations of tomography update. There's a new method called the joint inversion in the time-lapse tomography. As illustrated in Figure D, the joint inversion will combine both the baseline data and the monitor data together. Treat the baseline model separately from the monitor, run the tomography with a double amount of the input and the double unknowns. A cross-constraint between the baseline model and monitor model is applied to bring the similarity to the solution, but still, this method will create more air-post solutions in the inversion. We apply a double difference approach in our processing, like the one illustrated in Figure C. What it does is to take the difference between the inputs of the baseline and the monitor directly. Start the inversion with the baseline solution as a starting model, mainly to search for the model difference between the baseline and monitor. If there's no difference between the two inputs, there won't be a model difference from the inversion. So the solution for the monitor survey would be baseline itself. Thus, we will produce a more stable solution than all the other workflows, parallel, sequential, or even the joint inversion. The double difference FWI is similar like the double difference travel time tomography. The objective of waveform inversion is to find a solution that will minimize the waveform amplitude difference between the input seismic waveform and the synthetic seismic waveform. The synthetic waveform is generated from finite difference modeling using a given model. In double difference FWI, we measure directly the waveform amplitude difference between the monitor and the baseline. Again, if there's no difference between the input data amplitudes, there's no difference between the monitor and the baseline solutions. If there are differences between the monitor dataset and the baseline dataset, the double difference FWI will backward project the difference to a location in the model where it generated the anomaly, like a reverse time migration. We find we have more flexibilities to control where we want to monitor the model and where we expect to see the change. We apply the double difference FWI in a steam flood 4D processing. The objective of 4D time-lapse seismic is to characterize the steam chamber growth and conformance along the horizontal section for the operating strategy evaluation and the future infill program. The baseline 3D survey was acquired in 2015, and the monitor survey was the first 4D time-lapse seismic survey in the same area, acquired in 2019. Both the Weber size and the dynamite sources were utilized in both surveys at a spacing of 20 meters. The shot line interval is 50 meters, and the receiver line interval is 60 meters. Our processing workflow starts from raw shots. For the baseline 3D, we use the standard FWI workflow that consists of geometry validation, amplitude balancing, first break picking, and travel time tomography. The travel time tomography is to derive an initial model for the FWI. Our FWI is acoustic-based, so we carefully remove any elastic energy from the FWI input. Over the years, the topography and surface condition may have changed, so we calculate different residual status for the baseline and monitor survey separately to remove any differences caused by the near-surface conditions. For the monitor FWI, we use the double difference approach to invert the difference between the baseline and monitor, and then add the difference back to the baseline final model to get the final monitor velocity for PSDM, although the difference itself can be used directly for the steam chamber interpretation. Here is an example showing you how FWI algorithm converges until the field shot gather, shown in black, matches the simulated shot gather, which is shown in red. Here is an inline section to compare the monitor PSTM stack, shown in the upper panel, versus the PSDM stack using the FWI velocity, shown in the lower panel. The steam top and base are well imaged on the PSDM stack. Here's a crossline section. We see a good agreement where the observation well indicates no heating. You can also see the horizontal well pairs project onto cross section and a good agreement between the injector and the FWI steam chamber. Identifying where no steam is present has important value in placing infill wells. The FWI model difference in the upper panel shows even a higher resolution than the PSDM image at the lower panel. Our processing workflow for the steam flow study can be applied in the time-lapse VSP processing. Considering the target of CO2 plume is typically deep, and the plume is even below the bottom of the receivers, we have added more steps to run FWI. The model about the CO2 plume normally has no changes between surveys, so we will combine the baseline data and the monitor data together to derive a single model for the top part. The double difference FWI is only going to compute the model difference for the bottom part. We will start with the 1D model from the well log, add lateral velocity variations using the first arrival travel time tomography. I will use the synthetic 3D model to show why it's so critical to build up an accurate model at the top. The checkerboard model is more complicated than CO2 plumes. Here's a depth slice of the model at 1,400 meters below the sea level. If I slice through the model in the middle across the well, you can see the checkerboard anomalies are below the bottom of the receivers. The model above has only a lateral velocity variation below minus 200 meters. Assuming the FWI starting model is from the well log, it will not have any lateral velocity variation in it. I will show you a FWI result using this 1D model as a starting model. If I run a travel time tomography, the travel time tomography can add some lateral velocity variation below minus 200 meters. Using the travel time model as a starting model to run FWI for the top part of the model only, I can improve the lateral velocity variation further. Here is the FWI model at the depths where I have checkerboard anomalies. I ran only 15 iterations of FWI. Using a 1D model as starting model, you could barely see the checkerboard anomalies. I could run more iterations of FWI to improve the result, but if I run the same number of iterations using a better starting model that has the lateral velocity variation in it, the next slide will show you the FWI result at the same depth. Now we start to see the checkerboard anomalies. What we have learned from the synthetic model test, the workflow I have shown is very practical in production. It can help us to get a good solution at deeper target quicker. Tomo provides software and services to help you get the most out of your 4D seismic data. I have demonstrated with the 4D steam chamber study, Tomo's double difference technique is reliable and efficient, and can produce a high-resolution image to identify 4D seismic changes. I hope the workflow I have presented will help you in your 4D time-lapse processing. Thank you very much for listening. I hope you have a great time.